All right, we're getting started. I'm going to start, I'm recording, and we're just gonna kick it off. All right. So welcome back to the second of a three-part series about Apache Arrow DataFusion's architecture. I spent the last talk sort of explaining what a query engine was at a high level and why you might need one. This is going to be part two. I'm going to talk about how DataFusion's organized both from logical plans and expressions, and sort of how that relates to planning and maps back to SQL and stuff, and just to give a sense of how all the pieces fit together. You might remember, my name is Andrew Lamb. I'm currently a staff engineer at Influx Data. I spent a lot of time both on databases, and then I've worked on DataFusion for quite a while recently as well. So I'm very excited to know something about databases, and it's going to be great. So let's talk about how DataFusion works. If you might recall from last time, what pieces do you need to actually make a query engine, at least in my formulation? So you need a front end. As you might recall, a front end is the thing that translates like the SQL query or the description of what the user wants into a logical plan, which we're about to talk quite a lot about. So that tends to have a language parser and a semantic checker. So like making sure that when you say that you want a certain query, that it makes sense, like that you're not trying to compare a string to a number in a way that doesn't mean anything. Then there's a planner, which takes the parse tree, again, which we'll talk about a little more in a second, that describes the query and turns it into one of these logical plan things, which I'm going to spend most of this time talking about. Then logical plans is it's an intermediate query representation. So that means it's part of the path on the journey from having a string that describes a query and some type all the way to actually running the plan and getting the answers. So logical plan is one level. Most systems like DataFusion or other query engines are typically organized so that there's two levels. The exact line, is kind of blurry, but there tends to be a higher level representation, logical plan, and then there's a lower level physical plan. And it's just to keep the complexity separated. DataFusion's organized the same way, Postgres is organized the same way. The terms are different, but the concepts are the same. So the logical plan has an expression and a type system so that you can represent things, which we'll describe later, but like column equals a constant or whatever, but you need a way to represent the types of expressions that show up in queries. It is a relational data flow graph. Again, I'll talk about this later, and there's rewrites on it. There's also this thing I was referring to, a low-level query plan. I'm not going to talk about this this talk. This is going to be next talk, but I just wanted to give you a sense, right? Like there's this front end. We'll talk about that. We'll talk about how you get a logical plan, what you do with it, and then there's a lower-level thing called a physical plan. DataFusion also calls it an execution plan. Other systems call it something different, but it's a lower level description. It's still the same sort of type of calculation, just at a lower level. And it's lower level in the sense that it has details about statistics and sort orders and specific algorithms and that sort of thing. Yeah, and then there's of course the actual implementation of the work, like the things that actually do. Right? You've got these plans that say what the plan is, like what you should do, and then you've got the code that actually does it. So sometimes those are called operators. DataFusion, they're called streams. Well, I don't know if it's real hard terminology, but those are the things that actually allocate resources and churn through, lots of data with vectorized calculations and stuff. So we're going to talk about 1 and 2 this talk, and we'll talk about 3 and 4 I think tomorrow or the next day, part 3. So because DataFusion is a query engine, as you probably remember from the first talk, that means you got to map these pieces. So the front end, DataFusion uses the SQL parser Rust library. And so parse SQL statements end up being, this is the struct name SQL statement. We'll talk a little bit about that, but not too much. Remember, you don't have to use the built-in SQL one. You could build your own logical plans directly. Then there's LogicalPlan, cleverly named LogicalPlan, and Expr is the expression tree. Again, we'll talk about that a lot more in detail later. Then there's this physical plan layer that I talked about. In DataFusion, that's called execution plan and physical Expr. So those are the corresponding pieces from logical plan translate to execution plan, and Expr goes to a physical Expr. They might logically mean the same thing, but it's on the path towards execution. And then you have these operators, which, like I said, DataFusion, they're maybe called streams or sendable record batch streams or something. And we'll talk about those more in detail in part 3. So I'm now going to go through briefly a planning flow, and I'm going to use the same basic query, and I'll explain what it means a little bit more in detail in a second. throughout the rest of the talk. So in this case, this is a SQL query. It's like a string. First thing that happens, as I've been talking about, is that string gets parsed into a AST, which stands for abstract syntax tree. If you have a computer science background, or you can remember that far back in your training, that's just a tree of nodes that describes sort of a parsed version of this query. There's then a planning phase, which turns that parsed tree into a logical plan. If you're familiar with Postgres or whatever, I believe Postgres calls this the query tree, right? But it's the same idea. It's this high-level description of what the plan is. Then there's a physical planning component, right? Which we're going to end here before we talk in detail about this next time. But then that generates these execution plans. In Postgres, this is called an operator tree, I believe, or plan tree, access plan. Depending on what system, this concept is often called different things, but it's the same idea. It's a lower level description. And then there's the actual execution, which generates record batches. So that's like the super high level flow. Before I go any farther along with the higher level flow, I need to take a step and just try to make sure you understand what a record batch is, because that gets used. That's basically the unit of data that goes through all these different plans. And so you need to have like a high level idea of what they are. They represent basically tabular data. So it's like an Excel spreadsheet or whatever, right? Like whatever metaphor you like for a table with columns, named columns. I think with record batches is rather than having like the whole column or the whole table necessarily, it's some like sort of horizontal strip of it. So it's got some number of the rows. So here I'm trying to show that if you had a table sort of data like this in the left with two columns, right? The status column and the count column, and they had 4 rows apiece, you could represent this with 2 record batches. The first one would have the first 3 rows, right? That the color is trying to match up. And then the second record batch could have the last one. And there's no, it's your code can decide where the break is or whatever. But the point is both these record batches share the same schema. In this case, they both have a status column and a count column, right? The status column is a string array. It's what the Rustin calls UTF-8 arrow type. And then the count is a 64-bit integer. And they both share the same schema, but they have different sort of chunks of the data. All right, so that's important because record batches will be showing up a lot later. All right, so now let's move on to example query. I have worked with SQL for quite a long time, and so perhaps what's obvious to me might not be obvious to other people, and I wanted to make sure that we went over like what this query means, so that then when we talk about what the plan is used to that's used to calculate it, like that it makes sense to you. So this is a query. It has these different clauses. So let's say the first thing it has is a from clause, right? That says from what table. So there's a named table or a named data source, named view. Like this can be a bunch of things, but let's keep it simple. It could be a table right now. Here's an example of what that table might look like. In my example, I have 3 columns. There's a status column, right, which has some kind of HTTP status code. There's a path, which is the URL that was requested, and then there's a request size or whatever, which is maybe some information about how much data was passed in the request. The next clause in the query that you look at is the where clause. So this says I only want rows that when I evaluate this expression, path, which is a reference to this column, right, is equal to this constant. So what that means is the first thing the query is going to do is find all the rows from this table that actually, evaluate this expression where it's true. So in this case, if you look, I've colored all the rows that are colored are ones where the path is API v2 right, and the ones where the path is not API v2 right, I've left white because they're not going to contribute to the output of the query. Then there's a grouping clause. So there's a group by status and an aggregate up here. So what this means is that you have to take the rows that have the same value, and then there's a grouping clause column. It can be an expression, but in this case, I'll just keep it as a column. So you got to group the rows by value in this status column. And then you produce the status column and then some aggregates if you want. So in this case, I'm just going to count how many, this query asks to count how many rows were in each group. So now you might see why I've colored these rows green and this one blue, because the green ones have status equal 200 and the blue one has a status of 400. All right, so now the query results would look something like this. So now you have status, account, and then the corresponding rows here. So every group gets 1 row in the output. Hopefully that gives you a sense, because now I'm going to talk about how did this actually get planned, right? How did you actually create a query? How did DataFusion create a query plan to calculate this result? And so the first thing, so it used, let's start, the first part of the journey is to take the query path, the query string I showed you and turn it into a logical plan, right? Well, what's a logical plan? So a logical plan represents a data flow graph in the sense that it's representing data flowing. You read them from the bottom up. In this case, so the bottom, like the lowest part of the plan, when you look at them visually, is the data sources. So that's like where data is coming from. And then they flow up through these various other nodes in the plan tree, and they eventually produce the output. So the root of the tree, the one that's at the top of the screen, that's the thing that's connected to the client or whoever asked for the results. And all the rest of the stuff down below the tree is the way that the results are calculated. So in this case, you might imagine, right, the way that SQL query is translated into a logical plan is that the first thing it needs to do is it needs to scan the table. I'm imagining here it's a Parquet file, but depending on what data source that table was, right, DataFusion has all these extension points. You can plug in whatever you want, but in this case, I'll assume it's a Parquet file. So you get a table scan here. Then the next thing is you would feed the results, right, of that table through a filter node, and the filter node has an expression, right, which evaluates the predicate that I just described, right? So it's basically evaluating some expression and only passing the rows on that are true. And then it's got an aggregate node, which does the aggregation calculation I just described. So this shouldn't be a shock, right? Because I basically described the output of the query in terms of basically these steps. But I think this gives you a sense of like what actually happens. There's sort of a mapping from the declared description of what the query wanted to a sequence of steps like this. Right, logically speaking, what's passing between these nodes in the graph, right, on the edges, is like a table, right? That these are meant to be, they're called relational operators, is the fancy term for them. But what that really means is they take tabular data in, they produce tabular data out. It doesn't mean DataFusion like materializes the whole thing and the whole table between them, right? But logically speaking, that's what computation this describes. And while there's a lot more options, I think this gives you a basic sense of how a logical plan could be created and what it means. And again, I don't know if you remember, but if you saw the first part of this video, I showed some examples that showed textual descriptions or textual representations of these logical plans. And so you can see them as a user using the explain command. All right, so how does it go from SQL to logical plan? First thing that happens is it takes this string, right? I said it goes through the SQL parser library and you get a parsed AST out. I'm sorry, I didn't draw a beautiful picture, but like you could imagine this being a programmatic representation of this query, right? So it'll have representations for the from clause and all the crazy stuff that could be in there, and likewise for any arbitrary expression, and you'll have this sort of arbitrary tree. Then there's something called the SQL planner. And what the SQL planner's job is it takes the parsed tree, right? It takes this parsed statement and it produces a logical plan out. This logical plan is not super optimized. It's just like the basics. It's already pretty complicated to handle arbitrary SQL and generate plans that generate the right answer. So that the planner's goal is to get a plan that generates the correct answers that the user wanted. And it does not worry about lots of the fancier ways you might compute things. Because that is the responsibility of subsequent passes that we'll talk about. I also want to take a moment here to point out, I think I highlighted it last talk, but it's important to highlight again, while DataFusion has a built-in SQL parser and planner, right, that'll make these logical plans, you by no means have to do it. In fact, we have many users who don't use that SQL parser at all for that SQL planning process. Instead, they build the logical plans directly, right? So either they have their own query language, right, that they've built their own parser and planner for, or they have some other programmatic way to build up the desired logical plan. But once you have this logical plan, you can feed it into the rest of the DataFusion machinery that I'm about to describe, and it all works the same. Right? But getting the logical plan, you can use the built-in DataFusion one. Here's an example of using like programmatic. There's a data frame API as part of DataFusion. There's also like a builder API as well that you can use to make logical plans. And this is just showing like you can just skip all that and go directly to logical plan from DataFusion's perspective. We do this in IOX, right, with our own we have a couple of domain-specific query languages. I'm pretty sure this is how DataFusion works, and there's some other, there's a PromQL implementation, I think in GrabTime, that has a similar kind of thing where they use the rest of DataFusion, but they have their own planner for their own language. To give you a sense of the type of things you can put in a logical plan, there's actually, I did a version of this talk maybe 2 years ago, and I think there were 7 different logical plans, and there types of logical plan node, and now there's a lot more. So I'm just gonna like highlight, maybe point out a couple of these, highlight what they mean, but I'm trying to give you a sense that there's a lot of stuff built into DataFusion already, and of course you can always extend it with stuff if you want. So projection is the type of node that either does, projection is the fancy database term for calculating expressions, basically. So projection can be used to like pick a subset of the columns or compute things like A plus B or whatever. That's what filter, or like rearrange how the columns look or rename them or whatever. Filter is the classic filtering node, right? So what that does is it takes some number of expressions that each evaluate to a Boolean, and it evaluates that expression on each one of the input rows, logically on each of the input rows, and only produces at its output the rows where the expression evaluates to true. Not null, by the way. Null and false do not get passed through. The window operator is the window logical plan represents calculating window functions, which is that's probably worth its own whole series of talks of what those mean and how to use them and how they're implemented. But DataFusion has that. Aggregate obviously describes the aggregate operation we just described. You can do sorts, right? That represents sorting the data some particular way. Joins, with SQL joins, there's all sorts of fun about SQL joins. But there's an operator for that. Table scan represents data, scanning data from the table. There's some more sort of pieces here that are either important for helping generate initial plans from SQL queries or to help. So there's dealing with subqueries, with limits, extensions. There's a way if you can do distinct. You can put a distinct on the queries in DataFusion in SQL, and that will sort of remove all the duplicates. That again, like this gives you a sense of you're building logical plans up, or if you're imagining how that SQL planner works, it needs a fairly significant palette of operators to be able to compute the range of SQL and other things. So there's more, right? There's specialized ones for constant list of values and maybe settings. There's like statements, and DML is like inserting rows if you're trying to support some kind of database system. Analyze, explain have their own specialized handling. There's a bunch of them that deal with DDL. DDL is like a catalog manipulation. These probably, well, I'd rather those be collapsed together in some other node, but anyway, they exist. So I'm just trying to explain when it does exist. So anyway, the point is there's quite a lot of sort of things you can do that are built into DataFusion. And of course, somewhere in here, this extension, right? If you don't find an operation in here that you want, you can add your own extension node and make it do whatever you want. And again, like we use that in IOX, for example, because we have some specialized time series gap filling semantics that we want that are not general purpose, but can be described as a relational operator. So once you have this initial logical plan tree that describes, that might be fairly complicated because it's describing whatever arbitrary SQL query someone is passed in. It then undergoes a sequence of optimizer passes. So what an optimizer pass is it takes a logical plan in and it produces a logical plan out. To be correct, the logical plan output has to produce the same answers as the original input one does, at least according to the semantics of what same means. And then each one of these passes, the point of doing it is trying to make the plan faster or better, and it does a bunch of things. So the idea is you are keeping the results the same, but you're going through a sequence of steps to make the plan more efficient, right? And this is like where we've encoded all the logic that is important to run queries fast typically, but is not like super specific because a lot of it will make a lot of sense. So I'm just going to go through a bunch of the built-in query optimizer passes and just give you a sense of the kind of stuff that DataFusion does. You also, of course, can always add your own passes. So what are some of the built-in DataFusion optimizer passes? This is LogicalPlan, by the way. There's another set of them that happens at the the next layer, which I'll talk about next time. So the first sequence of things is push down. So generally speaking, the way you make execution plans, the way you calculate results faster is that you do less work. And so the way you do that is you tend to push the computation as close to the data as you can. That's not only is a distributed systems thing, and that's basically like the core query optimization idea too, right? You push it all down so that you can filter stuff closer to the source, maybe even in the source, or you can skip passing data around through the tree. That is often much faster. And so consequently, DataFusion has the classic push downs optimizations that are there. So push down projection means that if you're not using a column at the top, it'll push the projection all the way through so that column's not carried, it's not copied through the plan, but it's also potentially, if your data source like Parquet supports, if you only need 5 columns, but your file has 100, right? Parquet, you only have to read the 5 files or 5 columns, but it's very like the way the Parquet reader knows which 5 columns to read is that the query planner has to tell it. And the way Fusion does that is it applies push down projection. It pushes the projections all the way through. So it's just a sequence of algorithmic rules about when you can and can't push the projections down through. Likewise with limit, right? If you only care about 10 rows, there's no reason, and you have a file with 100 million, you shouldn't read all 100 million rows probably. Filtering is another classic one. You need to push the filters down as low as you can, because the earlier in the plan you filter out the rows, the better, because then there's not as much work for the rest of the plan to do. So that's like the core push down filtering. Basically, you pretty much need all of these to make any sort of query engine reasonably efficient. And so, these are very common, and the ones that I'm now about to describe start getting more and more sophisticated. So there's simplify passes that will try to get rid of expression evaluation during runtime, right? Think about the plan. It's like going to run on some large number of rows. And so if you can partially evaluate the expressions during planning time, right, once, you save a huge amount of computation during execution. So there's simplify expressions, which does stuff like, if you, extracted the day from now, or you're trying to subtract, now minus 5 minutes, or A plus B or something, you can calculate that once rather than for every single row having to recalculate it. There's a bunch of esoteric stuff about casts, which is related to when you're comparing a column to a constant value, you need to make sure that the types match up. So rather than coercing the types at runtime, you can do it once at plan time. I'm sure that's important. But it's kind of like this is the kind of nonsense which is not super intellectually interesting, but it's really, really important to get right in order to make your queries fast. There's obviously simplifications, which basically run through and figure out which one of the nodes, like if the nodes aren't doing anything, like it's a projection, it's just passing all the columns through because that was the most convenient way to create your plan. That's fine, because eventually it will get cleaned up by one of these passes. And there's a bunch of them. But wait, but there's more. So there's a whole sequence of steps related to subqueries. I'm not going to talk a huge amount about subqueries here because, again, it deserves its own whole sequence of talks. But subqueries are basically, you can put queries that refer to other queries inside it, and then almost always they're called correlated queries, correlated subqueries, so that the subquery actually refers to some column in the output. Semantically, what the SQL spec calls for is you're supposed to run the inner query for each row of the output query. Almost no execution engine that cares about performance does it that way because it's disastrous for performance. Instead, what typically happens is you rewrite the subqueries into joins, which it's as messy as it sounds. And so there's a whole bunch of different passes that'll actually run through the logical plan that gets created initially from the planner, right, which doesn't worry about correlated subqueries, finding and turning them into joins or whatever, and instead then there's subsequent passes which will find those subquery references and turn them into the appropriate joins. So if you see stuff like semi-join and anti-join showing up in your query plans, it's because you had a subquery that's been rewritten to one of those joins. And again, unless you love this stuff, I wouldn't worry about this, but it's kind of cool that DataFusion does it. There's also, speaking of joins, a huge number of things you need to do to run a join quickly. When I was talking about this 2 years ago, DataFusion had almost none of this, and it's gained quite a lot of sophistication recently. So in particular, joins, if you're not familiar with them, are like when you take 2 tables, you put them together, and you're trying to match rows logically what you're supposed to do is you're supposed to find all the possible combinations of the rows in the two different tables, and then only produce the ones that match some predicates, which are called join predicates. Which, if you did that naively, is a terribly inefficient thing to do. And so there's a bunch of sophistication involved with trying to find the right expressions. Yeah, and you push filters down, and maybe you can convert outer joins to inner joins, and a bunch of cool stuff. And then there's several, again, distinct also is something which can be very expensive to compute if you're trying to remove duplicates. If you're not careful, you can end up, well, you typically have to look at all the input data, or at least a bunch of it. And so there's a variety of ways to try to avoid doing that if possible, and also trying to use more efficient operations. So, the theme of this page is it's trying to let the planners create sort of a basic plan, keep the complexity in the planner under control, and then it's trying to go through and find patterns and pick better operations to compute the same thing, but faster. If you want to see how this stuff works, you can actually. It's kind of cool if you do explain verbose on the plans, like I showed in part 1 how to use explain. If you use explain verbose, it will in fact be quite verbose. It'll spew a whole bunch of stuff at you. But part of the verbose is you'll see each one of these passes, right? And it'll actually show you what the output of the plan was after each optimization pass. So you can actually watch your query get rewritten, which is kind of neat. Yeah, so here you can see in this case, you already see the projection gets pushed down, for example. All right, so I'm running low on time, but I'm going to push through for expression evaluation because this is important. So expression trees, I've been sort of waving my hands and saying Expr, expression trees, evaluating expression, all talk, but you need to understand what an expression tree is. But this is the Expr thing in DataFusion. It's very, very important. So let's say I have an expression like this. This is the value in this column, right? The path column where it's equal to the string. So that will get represented as a tree. This tree representation, if you've ever worked with expression trees or programming languages, this is sort of the standard way you represent an expression language like this. So there's a binary Expr node in this tree. Binary in this case stands for has two inputs, not that it is operating on binary as opposed to text data. In this case, it also has an equality, right? So it's got some operators, so equals. So you can use the same node for less than, greater than, whatever, and just swap out the operator. It's got two children. It's got the left child. In this case, it's a type of Expr called column, which is a column reference. So that's how you represent the path. And on the right, it has a literal. In DataFusion, literals are represented with something called scalar value. Of course, they're all typed. And so in this case, the scalar value is that string. So that's how you express this expression as an Expr tree. You can represent that. Yes, there you go. There's the equals, right? Probably guess there's the left path, and then the constant is represented there. So there's the programmatic tree representation of that SQL expression. I need to briefly point out type coercion, maybe because it's another thing that if you start writing a query engine, you don't appreciate why it's important until you hit it. So let's say you want to compute the square root of the value of a column. Turns out square root is typically implemented in terms of floating point numbers, but if your column's an integer, right, you have to somehow be able to call square root on this column that was an integer. So you can either have a whole bunch of different versions of square root, which might or may not be the right thing to do. In DataFusion's case, it goes through a process called type coercion. So type coercion will take an expression like this. So in this case, there's a func expr, right, which calls the function square root in the column. So this would be the Expr, the expression representation of the square root column. And it will actually add typecasts. In this case, it's going to add a cast to float so that the function, even though square root requires a floating point input and the column was not a floating point input, but this cast happens and the optimizer has, well, DataFusion has basically made the types all line up. It's important that the types, that you don't coerce stuff where you could lose data. Anyway, so we'll read the code if you care, but that's another whole thing where it's very important to do this. It's not super flashy, but very important to make something useful. All right, so let's talk about expression evaluation briefly. So because this is the last piece of the talk and we're already running a little late. So the way you compute things on arrow arrays, right? You talk about arrow arrays like arrays in memory. Maybe they've got numbers, maybe they've got strings, maybe they got whatever. Is that you call these things called kernels, which are in DataFusion's case provided by the Arrow RS library. But if you're using if you're using another language, other language bindings of Arrow have compute kernels as well. And the compute kernels are super highly optimized, and they're typically typed, right? Rest is all about being typed. So in this case, it's you can call EQ if you have two numeric arrays. You have to call a different one if you have a numeric array and a constant scalar value, right? Like a single value if you want to compare, for example, the column to 5 or something. There's other specific kernels for calling functions, string arrays and nulls, and it's not. So I think last time I checked, there's like 50 or 60 of these things in ArrowRS. There might be more. So there's a lot of them. Right? So what DataFusion's job is to take one of these arbitrary expression trees and basically call the right kernels, right? The kernel is super fast. You want that to go quick, but you need to be able to run it on some arbitrary tree. So I'll walk you through how that is done, and then we'll be done for this time. So Exprs, so here's the example we're going to use. In this case, it's the path equals the string, like I've just been referring to before, but this time I'm going to throw slightly more interesting. I'm going to say, or the path is equal to, the path is null. So it doesn't say path equals null because null semantics are special in SQL. So this is the way you would check if path is null. You can also, by the way, build these expressions programmatically. Here's an example of how to do that using sort of the Fluent expression API, which is just a fancy term. There's just a bunch of function calls you can call to build up the same expression tree. So you can take it as SQL, or you could have got it from somewhere else. Here's the tree that would produce this. Doing our same piece from before, you can see there's an OR here that corresponds to this binary expression here. The right-hand side is the path equals null, and the left-hand side is the path equals this constant thing right over here, right, which we saw earlier. So how do we evaluate this? So the way DataFusion evaluates these, I'm going to cheat, by the way, because the actual evaluation happens in the physical plan, the physical Exprs, but I'm like, so some other process actually happens between Expr and it turns into physical Expr before it actually executes, but this is still the same process still occurs. So I think it's still valid. We're just going to go through how does this expression tree get evaluated, and by calling the appropriate arrow kernels. So you look at the way it works is it recursively evaluates walking down the tree. So if you want to evaluate the total expression, you call sort of evaluate on the top node. The way binary experts evaluate their results is they call evaluate on the left input, on the right input, and then do whatever they're supposed to do. So in this case, the operator or this node would call evaluate on the left and then the right. So calling on the left would go into this binary expert that describes the equality check. That now, again, recursively calls evaluate on both its left and right inputs. In this case, you get to a column path. So it would look up that path, right, that column, and it would produce an arrow array. Let's say it looks like this, for example. They would now call the evaluate on this right-hand side is a way to represent scalar, right? So the values of this tree can be either arrays or scalar values. That's called columnar value in DataFusion. And then the binary expr equals is now ready to evaluate what it's supposed to do. So it actually has a giant dispatch loop in there that says, oh, well, given this thing's a string, and then I've got a string, type over here, it goes and calls the appropriate arrow kernel, which in this case was EQ UTF-8 scalar, I believe. And that we've over time moved some of this dispatch logic back into ArrowRS, but it's the same basic idea. He just calls the specialized code that then goes and does the very fast evaluation, and you get a Boolean array, right? Because it's comparing. So you're comparing two values, you get the equality, you get a Boolean value out. So in this case, you're comparing it to API v2 right. So you would expect the first row to be true, second row to be false, right? Because v1 is not v2, third row false, fourth row true, that thing, right? So that's there. And then likewise, now we've completed this recursive call. Now we're going to go recursively call that side. So in this case, it'll call is null. Is null will say evaluate its input. The input evaluates to this string array. This doesn't copy any values around or whatever. This just gets a pointer to the same string array that we had before. It evaluates the is null call by calling is null. Arrow has a fancy way of doing that that's very fast. And then in this case, there was nothing that was null. And then finally, you're able to call binary op-or, where it calls the fast arrow kernel to compare it to Boolean arrays, and you get the final output Boolean array. So that's basically it. I know I went over time. I'm sorry that was much, but I hope that was interesting to people to get a sort of a high level sense. And next time we'll talk in more detail about some of the details of how the sort of query execution path goes. So I think with that, I will stop the talk. Thank you very much. And if anyone on the call wants to chat or ask questions, I'm happy to take them. Thank you.
Okay.